I'm Barry. My background is in theoretical chemistry. I now work at ParityQC as a use case developer, and I'm also working on optimization problems.
I'm Josua. I have a background in particle and mathematical physics, and at ParityQC I work as a quantum software engineer focusing mainly on optimization problems.
Optimization problems arise in almost all industries, from engineering to telecommunications and commerce. In these problems, we don't only want to find a viable solution, but we often want to find the best possible solution. And this might involve additional rules for the problem too. To give a classic example, imagine you and your friends are visiting Austria and you want to visit the cities of Innsbruck, Linz, Graz, Vienna, but you're on a limited budget. And so to save money and fuel, you want to minimize the distance you travel. In this case, the rule is that you want to visit each city once, and the order you visit those cities will minimize your distance. So for this simple example, we could probably just find the optimum solution by drawing a map. But what if you want to have a more elaborate trip and go to every European capital? In fact, what if you wanted to visit every single city in Europe? So clearly this is a very important problem in logistics industry, for example, and solving it becomes much more complicated. For these larger examples, we need more sophisticated optimization solutions, larger computing power, and better optimization ideas.
It is likely that in the near future, quantum computers carrying out quantum algorithms can be used to solve large and difficult optimization problems. Various approaches and hardware platforms are currently developed, but for optimization problems, the basic approach is the same. The problem is converted to a mathematical expression for the energy of an arrangement of qubits. Solutions then correspond to an arrangement of qubits, some pointing up and some pointing down. The best solution is the lowest energy arrangement, which we call the ground state. The quantum computer runs operations on the qubits which aim to find this ground state. Quantum computers require problems to be given in a very specific form. A key step in our work as use case developers is therefore to translate optimization problems into this form. Different choices in how this step is carried out can lead to more efficient use of a quantum computer's resources. This is crucial for the current state of technology, because at the moment the number of qubits available and runtimes are quite limited.
Often, hard optimization problems involve many interconnected parameters. When converting this to a quantum computer, this leads to many connections across the qubits, across the device. This is where the parity architecture is beneficial. This allows us to convert the problem further and reduce it to only requiring local qubit interactions, which are easier to implement. Additionally, the locality allows us to perform quantum operations in parallel, reducing the runtime and therefore minimizing the chance of errors.
At ParityQC, we are building tools and designing software to make it easier to solve optimization problems with quantum computers. This will help us understand for which problems quantum computers can be more useful than classical computers. Once we understand this, we can unravel the full potential of quantum computing.